today we have, as speakers, we have our rocket team, our nationally award-winning rocket team, I should say, right here from Alabama A&M, the College of Applied Science, College of Engineering, Technology, Physical Sciences, here at A&M. And also we are most fortunate to have Angela Walker here from NASA, and she's going to come and talk about her tremendous and brilliant career. And this is inspiring for all of us to hear. So we're going to go ahead and get started, and what I want to do is allow Dr. Saif, come on up here. This is Dr. Mohamed Saif. He is the chair of the Mechanical and Civil Engineering Department here, and he's also the advisor for the rocket team. He's going to tell us a little bit about what they did and introduce the team.
Thank you. Good evening, everybody. Good evening. It's really gives me feeling of proudness to see that our team are competing nationally and proving that we can win. And in fact, this was not like something comes by luck or by chance or anything. You want to win, you have to plan it right, you have to do it right, and try to eliminate any source of negativity or any source of error that will hinder you from doing your goal or achieving your goal. The rocket team at A&M is new. We just started a couple of years ago. And as you can see, we have 3 rockets. The first one, the black one, 3 years ago, I tell you honestly, we won the second place. We won the second. And this rocket, the last year rocket, won the best looking rocket. Okay, we planned to win the competition. We planned really hard to win the competition last year. We didn't win because of the wind condition. Having that, we didn't pay attention to the wind condition, and this is why we lost last year. But at least we won the best looking rocket. So this year we said, okay, we're going to win the best looking rocket, and also we will win the competition. So I will leave that to the rocket team to explain how they won the competition. But as I mentioned that, I'm so proud of them because we were good listeners, we were good executor, and we have enthusiasm, and also we have the will and the energy to do the right thing and do it right. Without further ado, I would like to introduce the rocket team. We have 4 members from them today with us. Justin Taylor is the lead of the rocket team. Shaquille Dyer is the co-lead of the team. Julian Bell is a member of the rocket team. And Ricky Moorhead is one of the members in the rocket team. So I leave the floor now to Justin Taylor to start talking about the experience and how we did it so we can win the championship. Thank you very much.
All right, how's everybody doing tonight? Pretty good? It's a good day. Actually, it's a good day to launch a rocket today, too. Actually, pretty good. All right, my name is Justin Taylor. I'm a senior mechanical engineering major. And, yes, my name is Justin Taylor. I'm a senior mechanical engineering major. I am the rocket team lead. And on our rocket team, we're actually studying the dynamics and stability of the rocket. I'm Justin Taylor. It's Shaquille Dyer. This is Ricky Muirhead, and also Julian Bell. Next slide. Our mission is to design, fabricate a high-power rocket and send it to 1 mile and test a scientific payload inside. The rocket must return to the ground safely with 0 damage. We're also determined to be one of the best NASA USLI university teams at NASA. All right, this is our design constraints. Our first constraint is the rocket must reach 1 mile, 5,280 feet. Now, there are a lot of factors that cause us not to reach 5,280 feet. We have the total weight of the rocket, the engine selection, and also the wind speed. Okay, our second constraint is basically our rocket must have a safe landing. Basically, our kinetic energy cannot exceed 75 foot-pounds. So factors that contribute to that are basically the size of the main parachute and the weight of the rocket, as I said. Also, another constraint is we must have two parachute deployments, one at apogee and one around 500 to 700 feet. Okay, and our third constraint is basically our pressure on components, and basically pressure on the material, the diameter, the G10 fiberglass. It can be altered by the pressure. Next slide. All right, this is basically our stability analysis. You have our center of pressure located by the booster section. I don't know if you can see it with my razor. Yeah. Center of pressure right here. You have our CG, and basically these are the main components of the rocket. You have the nose cone. This is where the scientific payload is. You have the electronic bay. You have the drogue chute bay, the booster section where the engine goes, and the main parachute section. Next slide. All right, this is basically us building our rocket. Basically, it's straightly from scratch. We just build this, we get this material right here, these tubes, and this is us building it in the annex over there behind the ROTC building. So it's straight from scratch. It's not a kit that you buy. It doesn't look like that. It doesn't come like that. We make it like that. Next slide.
Hello, everybody. My name is Julian Bell, mechanical engineering senior here at Alabama A&M. I'm gonna briefly go over the recovery system of the rocket. So basically what it consists of is two events. The first event happens at apogee, which is the highest altitude the rocket will reach. This event will release our drogue parachute. Our drogue parachute is our smaller parachute of the two. And we also have another event that'll happen around 700 feet, which will release our main parachute. Now, what the events I'm talking about are ejection charges. Now, these are important because they actually are the mechanism that will break the shear pins that connect the two compartments. It has to overcome the friction of the two compartments and also separate about 6 to 10 feet. We developed these right here at Alabama A&M. They're live charges, and we have a demonstration for you. So everything happened like it was supposed to. That's for the drogue section. Now here's another demonstration for the main parachute. Yeah, so it's basically little sticks of dynamite that we create. Okay, so right here is our first rocket test in Manchester, Tennessee. All right, and here goes the results from that test that we actually got from inside the rocket. As you can see right here on this red line that kind of spikes right here was an error that we found inside of one of those ejection charges that I was just showing you. So we actually used this data to get our next test right. So, let me go to the next one. So right here is a simulation that we did for our second rocket test. Here goes the test of that flight. All right, and this is actually the results from inside the rocket. This graph and the graph I just previously showed you matched up perfectly, so we actually gained confidence in our simulations. And then this right here is basically our kinetic energy. In order for us to bring the rocket down safely, we can't have no damage to the rocket. If we do, that disqualifies. So we had to keep each section underneath 75 foot-pounds of kinetic energy. The rocket will break up in 3 sections. So as you can see, we achieved that goal right here.
Now that we have confidence in the accuracy of our rock sim simulations, there are 3 factors we have to look at to win the competition: wind speed, weight of the rocket, and the engine thrust. First, we have to decide a high-power rocket that would give us above 1 mile so we can adjust to it. Second, we have to determine the wind speed on launching day so we can weigh the rocket so that it would give us a 1 mile flight. Here is the L1420 that we decided to use, and the maximum altitude was 5,500 feet. The night before launching, we was denied the best looking rocket. As you can see, that white rocket is the best looking rocket. So we was determined that we were gonna win the launching because we was denied that award. Therefore, our current rocket weighed 45.3 pounds. We looked at the forecast, we saw that the rocket the wind speed would be between 8 and 10 miles per hour. We decided that we would go back to Rock Sim that night and we would adjust the weight of the rocket and see what weight would give us the correct 5280. And through the simulation, we decided that the rocket should be 47.3 pounds and we will get that 1 mile mark.
All right, now as far as we have the constraint of testing a scientific payload inside the rocket, this is the schematics of our scientific payload. We have a 9-degree sensor stick. This is it right here. It has 3 degrees of freedom for a gyroscope, 3 degrees of freedom for a accelerometer, and 3 degrees of freedom for a magnometer. The gyroscope measures dynamic movement in the X and Y, Z direction. The magnometer measures the magnetic field and the strength of the magnetic field in the X and Z direction. And the accelerometer measures the acceleration in the X and Y and Z direction. All right, this is basically how the components look. This is what they look like. You have your Adreno, your sensor stick. This is what it looks like that we have in the rocket for our payload components. All right, we have an onboard video camera on this rocket, the white rocket right here, Sovereign. This is what basically the transmitter, the receiver, these are our antennas. They have a range of 2 miles. So you got the transmitter, receiver, and the antennas, range of 2 miles. So we're pretty safe there. Next. All right, this is basically the data from the payload that we got from, you see the accelerometer, the gyroscope, and the magnometer. Next slide. All right, this is actually test day before we're getting ready. We're putting Sovereign together. We're putting shear pins in. We're connecting the nose cone, the parachutes, the shock cords. We're listening to altimeters. We're getting it ready for flight. All right, now Sovereign is ready. Everything is connected. We've ran tests. We've done everything we needed to do, and we're actually putting it on the rail. Once it's on the rail, we can't touch it. So this is us right here. This section right here, that's the last thing we can do. If it don't work, fine, we put it on the rail. All right, will AAMU perform? Everybody's watching. This was the last rocket on the launch pad that day. The team that was winning was Northwestern. They sat there the whole day until we launched. All right, this is one point of view of Sovereign taking off. You'll see another one on the next slide. It's right here in this section right here. See, I was actually the cameraman for that. I lost it in the video. I was so excited. I'm sorry. All right, this next video gives you a good point of view where you can actually see how high it goes. All right, here you go. It's over here. This is a little farther. I don't know, right here. Yeah, that's it right there. Now remember this location too it's gonna be a slide up this, but it's over here. Beautiful lunch, beautiful. If I was, it was beautiful. It was beautiful. All right, now I said it was an onboard camera, right, on the rocket. Okay, this is Sovereign's view. This is where Sovereign is seeing. It's looking at the crowd. This is the camera. I don't have good aim, but it's on that right there on the nose cone part. Now, you gotta look very closely. It's only for 4 seconds because the rocket after 4 seconds is at 600 feet per second, about 409 miles per hour. So look at it. You're gonna see it take off and it's gonna phase out because it's going out of range. Okay? So look real quick. You're gonna see it move. Just pay attention. Pay attention. All right, that's it. That's all. It was powerful. It's powerful. It went a mile straight and went that way. So, all right, next slide. Oh yeah. Oh, now remember our constraint of what I was talking about: kinetic energy, 75 foot-pound. We use 1/2 mv squared kinetic energy, right? We do not want. This is very important. This is if it doesn't come back around, it doesn't hit the ground with no damage. Basically, you disqualify. So, our calculation was our kinetic energy was calculated correctly, and watch this. Perfect landing, perfect. You can see it, it's gonna come over right, there it is right there. Oh, that's me coming across. Now y'all see that? It came within 50 feet of where it took off from. Very important. Within 50 feet. Nobody did that all day. It was by design. The way we folded our parachute and shot cords, it came within 50 feet of where it launched at. It's supposed to stay within 2,500 feet. We were like 50 feet from the launch pad. It's perfect. All right. Oh.
This is the test results of the L1420 that we have ran. This is the simulation that we've ran on the L1420 before launching, and as you can see, it got us to the point where it say, and this is the altitude of the rocket where the main parachute deploys at 700 feet and the different phases of the flight.
And this right here is the actual flight data. Now, if we had these graphs side by side, you can see they're basically almost the same.
All right, and yes, our rocket did perform. We were the team that got closest to 5,280 feet. We got 5,269. And Northwestern had waited all day. They had went over about 12 feet. So we were the last rocket to go, and when we went off, I'm sorry, we had to disappoint them for waiting for like 8 hours. Oh, and let me tell you, I was so confident. You see this poster board right here? I bought that the night before at 1 o'clock in the morning because I knew our simulations and calculations matched up. I had already knew we were going to win. That's not, we didn't find that. I bought 2 of them actually. I just didn't have enough time to write it down. So that's right there was hard work from the night before. I'm serious. I have the receipts. I can show you if you don't believe me. If you don't believe me, I have the receipts. Okay. And we would like to give a special thanks to Dr. Saif. He stayed with us for hours and hours for 8 months. He was a hard worker. I really like to appreciate him and thank you for being a great mentor for us. Thank you, Dr. Saif.